Okay. Well, I think actually we wove in a little bit of the agenda right into the goals of the workshop. So that I think it might make sense to start to actually just dive in. So here's that Google form on the agenda, although we can also try to, oh, interesting. Okay. Yep. I just caught up on the chat too, that the date isn't there. So, and I see Jome's on that. Okay. So, yep, I'm going to start this part. And so, it turns out building that template takes some time. There's a reason why we give students the template and you'll see it, but really the first about 20 minutes is building that template. So, all right, if you could join me in the Desmos classroom, so the participant side, if you could join us in there. And I even see that it says teacher Desmos, so we should get that changed. Desmos classroom. If you could just click on that link and I'll copy and paste that into the chat. Here you go. So if you can click on that link in the chat, you'll join me. I'll be on the teacher side of that. Oh, I see my spelling error there. Okay, so people are starting to come in there. I can see. You do need to click on the link in the chat and then log into Desmos. You can come in as just a guest. That might be the easiest. And just well, as people are logging in, I'll say a couple things. That Desmos is very case sensitive. You might be familiar with this with spreadsheets. Years ago, spreadsheets were case sensitive to uppercase, but that has largely gone case neutral. However, Desmos is still very case sensitive, and the funny part is it's lowercase. And so that's just a wrinkle that you got to remember. If you type in a function, we'll show some towards the end of the one, let's just say sign. Actually, sign works, I believe, case neutral, but it will not work if it's in this example, made up example, which is not good. I'll do RGB because that's true. If you do capital RGB, it will not work. If you do lowercase RGB, it'll work. So that's one. One that we want to say right up front, it's going to be in our troubleshooting section because that happens to students so much, but we've also seen it happen with just participants, is that equal sign is a command. So it actively sets something equal. And so many times if you set a number a variable equal to a number, it stops being a variable and it is just that number that it's been set to. So that can trip us up. So just be conscientious of that equal sign. Just a little joke there that, yeah, something can't be equal to 2 and 1 at the same time. So it will just give an error message. All right, so I see a fair number of people in there. So let's try out and build this template. If I lose you, the answer key is on slide 14. So we've done a couple of these now, and we got a pretty good pace, but there's no one pace that's good for everyone. If slide 14, so I'll jump into chemistry and jump to slide 14. So here, this is what we're going to build, but I'm going to now jump to slide 1. So we're just starting with the blank template. All right, so we're going to just build this template from scratch. All right, we'll do one last quick look here. There is a data table, although I think maybe easiest will be to just copy it from my screen. So let me get a data point or two ahead of you, but I can put this in the chat as well. That's kind of a nice thing that the chat has now allowed images. So there it is, but probably the easiest thing is that screen setup that we mentioned. Okay, so I'm going to go there and I'll go to full screen and I'll try to zoom in occasionally too. So here we got our blank. We're going to go up to the plus sign. So one of the first things that we need to do is get our data in here. So it defaults to X1, Y1. And so we might want to just change that right away. This was, we're doing an example from a temperature and pressure experiment. So here, temperature, we'll write T1, and then you can tab over, and here we're going to enter pressure data, and it's a data set. So Desmos was made by mathematicians. So you really have to have that P1. P for pressure is a variable, but this is actually a set, so it needs to have that 1. Okay, so the temperatures, in fact, I actually find when you have the whole thing, it's easier to do all the temperatures first and then all of the pressures. So the first temperature is 200, and then I just use down arrow, 250, down arrow, 300, down arrow. I get the drill, 350, 400. So we have our 5 temperatures, and then I'm going to go and click up to start entering the pressures, the corresponding pressure at each of those. The first pressure was 248, down arrow, 330, 382, 462, 520. All right, so we have our data in there, and it's worth just trying to show a lot of different things. The auto fit, this was a new feature a couple years ago, which was a nice lifesaver back then, and I know it's such a big deal in chemistry, and Joe might point that out again, but there's a couple other solutions now. In any case, anytime you just want to quickly zoom fit your screen, you got that magnifying glass, and once it's fitted, that magnifying glass disappears. So if you don't see it, it's because Desmos thinks it's already at the right zoom level. All right, so we got our data table. And then, as we so often do, we're going to enter, and, I just was at the biology Desmos, and they do it slightly different. That's the 3rd year. They don't want to overwhelm students with all of these formulas. There's a lot of different ways of doing it, but let's just show it so you can see it one time. So let's put in the proportional pattern. So I'm on a new line. I'm on line 2, and I'm going to say pressure. If pressure and temperature were proportional, let's put that in. That would be pressure equals some constant, as in constant rate of change, a slope, times the temperature. I am going to hold off because lots of times we like the slider at the bottom. So I'm going to hold off and just hit return, which gives, that auto made sliders, which is going to not be a good thing, actually. So I'm going to X those out. So I went down to the next line, and let's try linear. So that would be, that's your y equals mx plus b, but in context, that's pressure equals CT plus B. And again, I'm avoiding making the sliders quite yet, so I can have all the sliders at the bottom. So I'm going to go down to my next line, and I'm using my mouse to click in. It's giving me error messages. That's okay. Once I make the sliders, everything will be corrected. We got the pressure equals, this is that quadratic relationship, especially in chemistry when they're coming off of a year of physics. Nice to have it in there as an option. Maybe that helps them, think, could it be like that? Although I don't believe there is anything that's going to be actually quadratic in chemistry. All right, pressure, and then that last one, just for completeness, pressure is inversely proportional. That would be C, and then we use the slash, that question mark key that also has the slash. So that automatically puts it in fraction form for us, and we put the T. All right, now I will click on the slider for C, and there we go, it's there. Actually, but I still need B, so I'm going to go up to line 3 and click on B, and this is a great thing to teach right now. So we don't quite like B there. I mean, you could have a preference for B there, but I just want to show you, you can grab kind of like spreadsheets. There's just a lot of similarities. In fact, what I'd really have you think is this is very much a single column in a spreadsheet. All right, so in any case, I can grab the cell and drag it. So I'm going to drag it all the way to the bottom. And that way I have my two sliders next to each other. Yep. So, okay. Yeah, we're here. So let's do the sliders right now. I can see my B barely even registers on now it doesn't really look like I need it too much, but we just want to, that's what this webinar is about, learning all of these features. So B is, yeah, maybe we do want it to be negative. Right now it's just sliding between -10 and 10. So if I click on the little 10, it opens up a menu, and here I might zoom in a little. I don't know if I can do that one. Oh, I can't in this full screen mode. Okay, so I'm going to click on that little 10, and you can tell it, vary it between what? Maybe negative, I can just see on my screen right now, -100 and +100. Maybe that's all I need. Oh, I clicked out of there, so I got to type in 100. Step size. Sometimes you want to go by whole numbers, so you could put 1. Sometimes you want to go by tenths or hundredths. It auto tends to change the step size based on the range that you've selected. And I think from 100 to -100, it's going to force us to be a whole number, but I'm going to try it. I'm going to put in 0.1. Oh, it is letting us. Yeah, no, as soon as it gets above 10, yeah, it's gone. Yeah, so with that, when you have a range of 200, a spread of 200, it's going to go to whole numbers. All right, but in any case, here we go. Now we got ours. Ideally, we would like students to have their uncertainty bars before they do the best fit. So yeah, let's do that. Let's keep going in that order. So the next thing though, before we jump right to that, is we want to put labels on here. So the way we put labels on the graph is to put a point on the graph and then label that point. So you just visually look at this graph and kind of see about where I probably want to go over 100 and up to 600. So I'm going to type that in my new line. I'm on line 8. It always has to be parentheses. Just think from math class, X, comma, Y. So parentheses, my X is 100, comma, and what do we say, 600. Okay, so now I have my point on my screen. And you notice that once you complete the point, it gives you the option down here. There's a little label with a checkbox. If I check that box, it labels the point, 100, 600. But if I type words in here, so let's do, as in chemistry, the title. So we got the title here from the key, the behavior of 50 heavy particles. Okay, now that looks pretty small as far as the title goes. So I want to show you the options you have with text with labels. I'm going to keep calling that labels. So the only way to get text on the graph is to label a data point. So if I go over to the blue, there's kind of the blue button on the very leftmost column by the number 8, and I click, and you got to hold it for 2 seconds, and it pulls up this option. So here we can change the color, and maybe label is black. And then the other thing that you want to probably use pretty often, there's 3 things. You want to choose your color, you want to choose your font size. This was made by mathematicians, so they're clever, and call it scale factor. How much do you want to scale those letters? So you want them twice as big, 3 times as big. I'm going to make it 3 times as big. That's nice. And one last thing that we want to do here is, it's just always so nice to do it, is turn on the drag. So once you click on drag, now that title, you can drag it around on the screen. And that's going to be really nice as we learn to resize. And I'm going to wait to resize until I have our uncertainty bars. Okay, so there's our title. Draggable, very nice. I'm in line 8, I'm going to hit returns to get a new line. And the other piece that we want is our best fit mathematical model. What was the equation that was acting like our system here? So I need another point. So I'm just going to, again, parentheses, 100, maybe 600. Now that I've dragged that other one out of the way, or just in case you haven't dragged it out of the way, I'll do 100, 500. Sorry, 100, comma 500. Turn on the label. And I guess, yeah, we do kind of really want our best fit mathematical model. So I'm not going to drag it out because I actually happen to be pretty close on that. Seems like it's a proportional fit, something around, oh, I was going to check our key just so it is exactly the same. That's nice. Whoops. All right. So that best fit is that red line. And again, ideally, students would have uncertainty boxes before they did this, but it's such a good fit. I think we can be comfortable with that. So pressure equals, and we suggest, especially in physics, that they write out not just P equals 1.3 times T. Just a lot of students forget what that P is, and we don't want to lose them. Experts shorten things, but I got to remember some better acronyms. But like if you say like the NGSS, PEs, and then we got to combine them with the SEPs and the CCCs, right? Like when you start hearing these acronyms that don't mean, or they're coming at you fast and furious. And that's what a lot of equations look like to students. So we can moderate that a little bit by writing it out. So the pressure equals, and at this point, they might not know what C is. So it's good to write that actual number there for the time being. It's 1.3 times the temperature. And this is a starting spot for their data discussion. Okay, again, that one's pretty small, so I'm going to click and hover on the green button. I might want it smaller than the title, which was 3, so I'll make this one 2.5. I think it's always a nice touch to color code it to the best fit line. So our best fit line was red. Maybe it makes sense to have the mathematical model in red. And then I do want to make it draggable again, and that way we can drag that and have the title and the mathematical model up there. We're going to resize this again, so I won't overdo that. Okay, so we're there. Really, the last thing left is to get the error bars, and that's going to take a little bit, but we can do it. So I'm going to say something, I'm going to try to give a verbal description and then start the coding. So the first thing, though, that we need to do is tell the computer how big the horizontal uncertainty is, our error bars. So our horizontal, we're going to write, oh, good. Actually, I'm going to show this. I'm in a new line, and just like Excel or spreadsheets, this sort of defaults to already having an equal sign in it. So if we want just regular text, we actually need to tell the computer we're just going to use simple text. So I'm going to go up to my plus sign here, and I'm going to select note. That way, it just knows it's simple text. And that's also shown by the quotation marks that now appear on the left side. Now I can write horizontal, and it doesn't think I'm trying to program it. So horizontal error bar. Okay, so that's our horizontal. In this case, that was the temperature measurement. I'm gonna just nope, that was our temperature measurement. That's what I said. Good. Okay, and then hit return for a new line. It defaults back to a command line. And we, it's just a simple one. We actually use U in the template, but here I'm just going to say H. Our horizontal uncertainty is H equals, and just from the answer key, it was about 5 degrees. So their horizontal uncertainty was about 5 degrees in the temperature. And then, no surprise, probably, let's do the same thing up vertical. It's not liking this. It's thinking I'm trying to do a code. So I got to go up to the plus sign and say, hey, this is just a note. because I started typing, it made a new one. So if it's empty, it'll just change the line you're on. But here because I hit the plus sign, it went to the next line. Okay. So then I'm back to typing in vertical error bar. And of course, if you put those two error bars together, they make a box. And a word choice that students seem to understand a lot better is the uncertainty boxes. That, each data point has a little bit of uncertainty in the temperature and the pressure, so it traces out a box. Nice. And here, just to keep it one letter long, let's call that V. V equals, and in this case, the pressure had an uncertainty of 30 kilopascals. So just 30. Okay, now we've told the computer how big the uncertainty is in the temperature and the pressure. Now this is where I'll verbally describe what we're doing, and then I'm just gonna write the code and then talk about the code, because it doesn't make sense to talk about a piecemeal. So now we want to go tell the computer, go to each data point. You can see this data point, this data point, this data point, this data point. Go to each data point, and let's start with the right uncertainty bar. So let's go to the data point, and that is, up here at the data, T1. That is our temperature for each data point. And to draw the right bar, we should add our horizontal 5 degrees. So if the temperature was 200, we want it to go to 205 and draw a vertical bar up and down. And that, of course, it ought to be at 248 plus or minus the vertical uncertainty, that 30 kilopascals. So we're going to go code this Desmos to do that. Okay, so we need a name. I'm going to type R for right. We're making the right side of the uncertainty box. And just to show this, we don't need this, but this is our right uncertainty bar. I'm going to show you subscript. So when you're in this mode, if you hit shift underscore, the key to the right of 0, and then we can label this right bar. Sometimes you just need to subscript. If you had multiple pressures, P1, P2, P3, with a number, it knows it'll actually auto subscript it. But if you want to label your variable a little bit more, right, and then have bar, that shift underscore is what you want to do. Now I want to get out of it. So I'm going to hit right arrow, which returns me to normal text, and then equals. Again, we want to go to each data point. So I'm going to type T1, and it's telling me, hey, there's 5 elements. Yep, there's 5 data points. Okay, so at each T1, I want to add my horizontal uncertainty, H. And now that gets me to 205. And now I want to draw a vertical line. And this one I'm just going to write because it's an inequality, and I want to say it. I'm going to write it. So no surprise, P1 minus the vertical uncertainty. We want to plot values of Y for that. So let me say what I'm doing. So I did curly brackets, which I did learn a couple webinars ago is technically called braces, but those curly brackets, that's what shift curly bracket key, and then P1, and I want to subtract the vertical uncertainty, so minus V, and then I want the less than key, the one to the right of M, and then equal sign, and that makes it less than or equal to Y. And then I also want Y to itself be less than or equal to P1, the corresponding vertical pressure, plus the vertical uncertainty, plus that 30 pascals. So that's plus V. And we want to use V instead of 30. We could do 30, but if we put in V, that keeps the slider active. So there we go. And if I wiggle my V, the vertical uncertainty, you will see the bars grow and shrink. So that's where it's just nice to put it in terms of H, or horizontal uncertainty, and V. And of course, by using T1 and P1, if we added data points to our table, they would pop up with the uncertainty boxes around them. Okay, so you're probably gonna be ready for this. Let's do the left bar. So I'll use capital L underscore BAR, right arrow to get out of it, equal sign. So we want to do the left bar. So again, let's go to each T1, each temperature data point. And this time, instead of adding, we want to do the left. So we want to subtract the horizontal uncertainty. So there, it's getting us in the right spot. And now we just want to draw a vertical line for the corresponding pressure from the minus the vertical uncertainty to the plus vertical uncertainty. So I'm just going to type that out, curly brackets, braces, P1 minus V, doesn't even change, less than equal sign, Y less than equal sign, P1 plus V, curly brackets to close it out. Nice. Now, something we don't like, or like, see how they're all different colors? That's just because Desmos is randomly assigning colors. So I might keep them all green. So I just, again, click on that purple dot and select green. And that way, those will be green. Excellent. And now, of course, we got the top and the bottom. So you can kind of expect things are going to shift, right? Now we're doing a horizontal line. So I'll do T for top underscore BAR, right arrow, and equals. And this time, now we're doing the horizontal. So we're going to flip it. We're going to do P1, right? So now I'm going to each pressure, and I want to do the top. So I'm going to add the vertical uncertainty plus V. And now that I'm sitting above each data point, I want to draw a horizontal line from the temperature at that data point minus the uncertainty in the temperature to plus the uncertainty. So I'll do braces T1 minus H, the horizontal, less than equal sign X in this case. And you can see I've only bounded it on one side. So it's going from negative the H uncertainty to infinity. We don't want it to keep doing that. So I'm going to say only plot that for values of X less than or equal to T1 plus the horizontal uncertainty, curly brackets. Oh, I missed a 1, so it doesn't know what to do. That's why it's giving me that triangular error. So if I put my 1 in there, boom, there it is. We got our top line. And again, just to show it off and give people a chance to catch up, if I change the horizontal uncertainty, you can see everything stays together. And I forgot what this was supposed to be. 5, yeah. So I'll set that back to 5. And you can anticipate what's coming next. We need our bottom bar. So I'll do B underscore BAR, right arrow, equal sign. And again, similar, go to each pressure data point, and this time subtract the vertical uncertainty that gets us below each data point. And now I want to draw a horizontal line correctly. So I'll go ahead and just type that in there. T1 minus the horizontal uncertainty less than equal to X. And again, we have that going off to infinity. We want to restrict its domain. So put the equal or less than equal sign T1 for each temperature data point plus the horizontal uncertainty. And there we go, curly brackets to end it. And again, now the question is, I'm going to change this one to black. And that way it just shows a little bit the difference between horizontal uncertainty and vertical uncertainty with the color coding. But sometimes visually, you know, most apps would have them all the same color. So that's an option for us, whatever is your preference. All right, there we go. So we got our uncertainty. Now let's go back and just fine tune this. And I want to just show you, there is a new feature that everyone loves for resizing the screen. Sometimes we lock the screen, and Joe May will show you that in a couple slides here, but sometimes you do want students to adjust. So there's a new great feature for that. But first things first, now that I got my best fit line, this is debatable. I've gone the journey of, I started off just having people unclick the line, and that green parabola, that's not going to be our best fit. You know, the inversely proportional, no way. So you can unclick them and make them disappear. That has the benefit that if they mess up, they can just re-click it and bring it back. I have been convinced myself that, but students sometimes are confused. They see 4 equations over there. We go ahead and just X them out now. And if they do make a mistake, there is an undo button up here. Now, if they, you know, obviously if they do it and then do a bunch of other things, sometimes they just need to start over on the Desmos if they've messed it up too much. But we're about to wrap this up, and we're going to do much more rapid fire after this slide and the next slide. So in any case, I do like Xing them out, but you'll have your preference. So there you go. We got our equation. We got our things. So here, I just want to show this. If you have your cursor and you see it's just an arrow, if you go near an axis and then you hold down shift, your cursor will turn into a stretch arrow. And you can now just move your mouse around and it'll only adjust the vertical. You can actually do this anywhere. Anytime you put shift, it'll turn into a stretch arrow. If you're not near an axis, it's at the 1-to-1 ratio. It equally does. It's like stretches X and Y. Okay. And of course, if you go down to the X axis, it'll stretch just the X axis. Now, I also like the origin to be kind of in the bottom left. So I'm just going to click and move the whole graph down to the bottom left. And now that I'm here, we want the data to take up most of the screen. So I'm going to stretch mine horizontally a little bit. We like to see a little bit past the data points. That's good. That actually looks pretty good. That's just in the realm of looking good. Maybe I'll stretch it vertically just to show off that you can do it. Okay, that's good. The one last touch, which again is just maybe a personal preference, is see the dots. And the fact that the pressure just kind of zoomed to the right there on me. I like to turn the dots off, and you can do that just by a simple click of the dot. Now it's still draggable, so I can grab it and put it wherever I want. But when you do turn off a dot, sometimes it auto moves it a little bit. But in any case, now here I got it. And that's going to now make a pretty good screenshot. And that's ready to go. How do you get the stretch? Yes. The stretch is you use your mouse and you hold down shift, and your cursor will change from a cursor that grabs the graph and moves it around. If I hold down shift, it goes into stretch mode, and the cursor changes from a cursor arrow to a double. Cool. Yep. Yeah, that is so good. It's so nice. And that has made a world of difference of getting students to have just a pretty good looking graph that they can screenshot, or there's a couple ways of getting it into their lab reports. Okay, that's great. That's it. That's the template start to finish, right? We started with a completely blank one, and this is the final product for your lab. So hopefully maybe that's only something you need to do one time in your life, but now you kind of seen start to finish, a peek behind the curtain, and that is helpful to you. All right, so we wanted to break this up. We could actually do it right off of this slide. So want to show you one more feature right here. And just in case I lost anyone, or I know, yeah, internet connection, right? Like we set up slide 2. So if you want to stay on this slide, sometimes you just like working on the slide you made from scratch. So you can stay here. But if you got behind or your internet dropped, meet me on slide 2. I'm going to go up to the right here. And this is a feature of Teacher Classroom. I'm going to go next. And again, remember, the answer key is good. I think I want to say 14, but I want to now say 15, right? So thought I fixed that, but let me just check slide 14. Yeah, sorry, this is 15. But if you want to see the answer key of what we're about to do, it's on 15. I want to show you something pretty neat. This is something that, like, if you finish with 10 minutes fast with a period, this is a great, and you're already in Desmos, this is such a great thing to do. Or you use the confidence, and this will work for many things, but I'm going to show you a great application of it. Okay, I want to teach you how to insert images onto the graph itself. So we need an image. I'll copy and paste it, and it's on the agenda, but let me put it into the chat. So here is an image. You're going to need to download it, but the link is in the chat, and I'll click on it showing you. Here's that confidence matrix, and then I'm just going to hit the download arrow. So it goes into my downloads folder. Okay, it's there. And I'm just in a new line. And I'm just going to go up to plus. And there's actually a choice for image. So we just select image. It's that easy. I don't think you can see it, but it just brings you to your file manager. And mine just brought up the download, so I can see my matrix right there. So I'm going to click on it, and it's there. Oh my gosh. It's there, but it's tiny. So I'm going to zoom in. Okay. Great. So there it is. That's how easy it is to do an image. Now, usually almost all images you're going to need to do a little bit. So let's talk about it. When you first put it in and you click on the image, you see these sort of outline dots. Those are very useful. So if I click and drag on them, I can resize it. That's important. I want to resize this. I make it wider. 45 degrees makes it taller and wider. And I'm going to zoom out now so I can get back to my data. And I'm going to keep making the image wider as I do that, because I got a plan. And this might be a little bit difficult. I ultimately want to I'm going to zoom in. If you're familiar with the confidence matrix, one of the columns is when you make a prediction that is in your data range. So let's quick look. Our data range was from 200, temperature of 200, up to a temperature of 400. Now I want to make that column the same width, because there's something neat that I'll teach you a lot about Desmos and show you something you could actually use this for. Okay, so I want to get that wider. Okay, that's getting pretty close enough. Now I want to drag this image itself, but I just want to warn you, you can't resize and drag at the same time. So now that I've made I'm going to make this even bigger. All right, now that I have it roughly the right size, I'm going to go over to the image and click on it's not a color like our error bars are above. It's actually a little picture of the image. So if I click and hover, it brings up that menu. And I'm going to click on draggable. It's kind of funny. Draggable is different every time, but it seems like sometimes it's a slider, sometimes it's a checkbox. Okay, but anyways, now that I clicked on draggable, when I drag it, now I can drag my image. So I'm going to drag this over. I'm going to zoom out. And I just want to drag the confidence matrix below the x-axis. And now I want to resize it, but I'm in drag mode. I'm clicking on it. Nothing's working. That's because I'm in drag mode. So you can see there's a little bit of work, but it's not too bad. So I click over here, turn off draggable, And when I click on my image, my resizing chart's back. So I'm going to do 45, and then I'm going to make it wider. And we don't need to overdo this. Okay, but that's, oh, and I wanted to drag it, but I can't drag it. So now I got to go back over, click and hold on the button, bring up that menu. And someone said this in our last Desmos, you might have especially a touch screen. There's a fine line between clicking on the circle and bringing up this menu. And sometimes Desmos thinks you want to drag the cell around. And we've heard it a couple times. It depends on your computer. Some computers are really finicky, and you got to be in the very, very center of the image and hold down for 2 seconds before this menu will come up. It was driving people crazy. So that's happening to you. Know that that's Desmos and your computer. Okay, so I am going to click on draggable, and I'm just going to try to roughly line up. You see, I'm just trying to line up this. Oh, and now I realize I made it too big. Okay, I'm only going to do this like one more time. So, all right, so now I want to resize. This is actually really good, though. This just shows you. I'm going to take off draggable, and I'm going to just horizontally. I'm going to try to get that to be about right. Good. Now I realize it did it to the center, so I turn on draggable. That's good enough. Okay, there we go. Good enough, right there. Cool, but you can kind of see that the column in our confidence matrix says data range, and the width of that column is close to the width of the actual data range on my graph. But we can go one step farther, and I just want to show you how you can use an image and combine it with some shading on the Desmos, and then we'll call it a wrap for doing the coding ourselves in Desmos, except for a fun feature. Okay. So we got it. Now I just want to teach that fun feature. Now, sometimes students, just aren't seeing the connection. So you can just see that this is color coded, right? When your confidence is high, it's dark blue. When your confidence is medium and you're starting to predict for higher temperatures, your confidence might change, right? The vessel might start to leak at higher temperatures and pressures. So this best fit line, this mathematical model may not apply. So our confidence drops. And of course, if you get really far away, I mean, all sorts of things can happen at high temperature, right? The material starts to degrade. Pressure is so high, yeah, it could leak again. Okay, so let's do some shading to see that. So just for fun, to show you a nice little feature, let's start off as simple as possible. I'm going to use generic X and Y here. Just Desmos, there's sometimes that the only true variable Desmos will recognize is X. And I'll show that in a second. Okay, so in any case, I just want to start with X greater than 0. Oh, I got to drag my graph so you can see. So this is all values, right? Like infinite, all values of Y, but X is greater than 0. That's what quadrant 1 and 4 from math class. All right, that's a little more than I wanted. And I also want it blue. So the first thing I'm going to do is click on that green dot. I'm going to change it blue. And since I'm here, I want to do it now. You can see the fill. Sometimes it's called opacity. Sometimes it's the fill of the color. All right, so it's at 0.4. I want this to be my darkest one. So I'm going to go to 0.8. Yeah, that's a nice dark blue. It'll get lighter once we click off of it. It's kind of extra dark because it's selected and it's blue. Okay, but that's coloring too much of the screen. We want to restrict the domain, just like we did with our uncertainty bars. So I'm going to do curly brackets, and I only want to do this for values of temperature, but that was our X. So temperatures, what we said, 200 to 400. So I'm going to do 200 less than X less than 400. And that's nice. Now we got this nice blue column. Now, right now it's going infinity to infinity, and maybe that's too much. right? But that is kind of nice, especially if we put this image in front, but that is a little too much. So let's also restrict it in the vertical direction. So again, you want to restrict the domain, use the braces or curly brackets. And we want this for values of y. So 0 less than y. And then this is the one where you have to use x. Less than, and we want to tell it to go less than our best fit line. So I'm going to quick look up. Our best fit line was proportional CT, but I'm going to use CX. And that's nice. And then curly brackets to end it. And then I'll click away. Nice. Okay, so that's the area of this model that we have high confidence in. And you can kind of guess, once we get past that, we might want to go to a lighter shade of blue to indicate that when we go beyond the data range, it is a little bit less confident. So I'm going to get a new line, and then this is really just practice. So we get kind of 3 reps in here. X greater than 0. And it went purple on me. So I'm going to click on that blue dot, change it to purple. And now I might want the fill to be a little lighter. So I'll do what? 0.6. And again, that's too much fill. So I want to restrict the domain from, that's jargon that they learn in math class. So here, now the question is, what should the domain be? And this is just, there's no right answer. There's thoughtful answers. And so it's beyond 400. So it's like 400. And technically, I guess we could even make it less than 200. But okay, 400 greater than x, or sorry, less than x. And then how much more temperature does it go up where you'd have medium high confidence, right? I mean, it's a little bit. It's not like at 401, all of a sudden it's going to spring a leak, or it's not very likely. And, you know, it's a judgment call. I actually call it a really good thing. This generates discussion with students. And I'm not really sure what one is. So maybe we'll say just 100 degrees. So 500, because above 500, maybe we're starting to get worried. Curly brackets. And then, of course, I got to restrict the y domain. So we're just getting our practice. 0 less than y less than cx in the curly bracket, and click out of there. And then we'll see, nice. So the shading gets a little less. And then, of course, we're getting close. We can probably wrap it up, but let's just, for completeness, do one last one. X greater than 0 for the, predicted range is far from it. This time it went black. Click and hover, turn it to blue, and the fill probably, could stay at 0.4. That's probably good. And restrict its domain. We went up to 500 before, so this time we should start at 500 less than X. And maybe this goes to infinity. I don't know. I don't know where to end it. So maybe, but all bets could be off at a certain temperature, right? When, and this is just a little bit of a guess when that thing is going to melt or do any of the other things. In any case, just to wrap it up, I'll say 700 degrees, curly brackets, and then restrict the vertical domain, 0 less than y. And I know I'm going fast, so if you're trying to keep up with me, I'll pause after doing this. Check the chat and all that. Okay, there we go. So, and if I click out of there, that's that lighter shade. So here's just, having images is super powerful. And if you teach students to do it, like with this example, later they add a lot of other things. It's kind of fun. Students will sometimes add a picture of each data point. I know in the biology class, they sometimes have that foam. They take a picture of the height of the foam and they just put it on the graph. And that's good stuff, right? That's a student that might finish early, kind of built-in differentiation. And that's helpful. And it's kind of neat to see. So that's just a really great resource to be able to add pictures. There's just so many different times where students could add pictures. Then we also showed how to add shading to a graph. And in this case, making the shading match the shading of the confidence matrix to really let that sink in. And now, that's another reason to make everything draggable, is we can move that title and best fit line. And that's pretty cool. Okay. With that, I'm going to check the chat. And we knew that was a big big one. So we're gonna pop out to the agenda. We're gonna take just a couple minute break here to let you, yeah, just stand up, connect possibly with a colleague, and then we'll start. Jomay's going to start back up, and we're going to target some of the semester 1 labs, and talk about the troubleshooting and just some really easy, yeah, let you think about teacher moves that you can do to enhance student understanding with Desmos. Okay, so we didn't have a yep. So we'll take what? Just check in with Jume.
How about 5 minutes? Everybody take care of their needs.
Yep. See you back here. We're at that halfway mark. 5 minutes. See you at 5:05, and we'll start up with build an atom template with Jume. All right. If anyone, I'm just going to hang out here. So if I lost you on anything, where there's the answer key on slide 15, and let me know, though. Glad to help if you got a question. Superscript, yes. Superscript is, it depends if you're in the math mode or simple text, but I'll just quick jump in there. I'll just get to a new line. If I were to want to do quadratic, like P equals C T, if you want to do superscript and I'm in math mode, you're going to do Shift 6. And that puts you into superscript mode. So if I start typing, I'm up top. In fact, I could write a bunch of stuff, but yep. So Shift 6, that little caret, puts you in superscript mode. And now if you're in text mode, you can't. And that's the problem with simple text. So a label, when you label a data point, or are making your title, if you want a superscript, there isn't a way. There's like a little workaround where you can add a second little one, and you can change its font to be small, and you can do it. I've seen students do that if they really wanted to, but simple text is just simple text, like even on your cell phone, the same thing, where you can't subscript or superscript.
Bradford, is it okay if I share my screen now?
Oh yeah, definitely. I'll stop.
Okay, one more minute, everybody, and we're get started up again. All right, everybody, we're going to go ahead and get started again. So we've gotten a chance for you to build a template from scratch for Gay-Lussac's law. That is the graph that it is in Unit 1. And I do feel like it's helpful to go through and build all those formulas once, because when you get into a troubleshooting situation, having done that once before, it will certainly help you, especially, you know, we tell students uncertainty not for editing, but inevitably students will open up those boxes sometimes and make edits in there, even though we don't want them to. So now we're going to shift to Unit 2. So in Unit 2, students do an experiment called Build an Atom. And so what they create, in a sense, is a mini band of stability. So they plot the stable isotopes for elements 1 through 10. And so that's what you are seeing if you go to slide 3 in the student version of Desmos. So it should look similar to what you're seeing on the screen here. So we've already gone ahead and plotted the data for you. So most of the isotopes have, or most of the elements have 2 different isotopes. A couple have 1, and I think 1 or 2 have 3. So we've plotted all of those on the screen for you. And so now we would be at the point where the students are getting ready to, graph their data. And for students, when they come to this graph, this is the first time that they're really seeing a scatter plot, and they're really trying to do a curve fit in a scatter plot. So one thing that I tell students is that it's helpful for them to think about, if we were to draw a cloud around all of the data points, we really want our line of best fit to kind of go through the center of the data points. So just take a minute right now to kind of adjust your line of best fit. Remember that you want to use your C slider and your B slider, and try and really get that line of best fit to really go through the center of that cloud in which our data points would be. So I'm going to pause for a minute. Okay, hopefully we've had a chance to adjust that a little bit. So Bradford was talking about preferences of leaving formulas in versus just unclicking the colored dots. I usually advocate that students just unclick the dots. The reason that I do that, and we'll see in the next slide as well, when students get to exponential decay, they really want to fit that with inverse. And then as we talk about the function more, and they talk about their look at their data set more, they realize that inverse is just really not a very good fit for their data. So I always encourage them to just unclick the dots. I said, because you never know, you might change your mind later on. So we're going to get rid of those other lines. I'm going to move my C slider here. And one thing I notice as I'm starting to move my C slider here is that it's just really difficult to get my line of best fit to kind of go through the center of my cloud, if I'm thinking about these as being the tops and the bottoms of my cloud. So I am going to have to put a B value in. And so I'm going to have to move my B value down a little bit. Okay, that's going a little bit better through the center, but now I definitely need a little bit more tilt on my data points there. And another thing that I tell students is that basically they're trying to equal out the amount of data points above their line of best fit and below their line of best fit. And that helps some of them as well. Now, the error bars in this particular investigation are representing not really error in the isotope, but just the fact that the element can exist sometimes, at least in the first first through 1 through 10 elements with one more or one less neutron. And so that's how we're accounting for that variability in the number of isotopes that's present for each element. So we don't have a horizontal error in this case because each, number of protons is unique for each element. And, that is, not going to have error. So and that happens in chemistry, I'd say with several of our experiments where we might have error for one variable and not for the other. So now we've got our curve fit there. We've got our line of best fit. And so one thing that I really try to emphasize talking about when we are doing this board discussion and really analyzing our data is that we really can't have an element until we have one proton, right? If we have a neutron, if we have an electron, they're subatomic particles, but it doesn't constitute actually having an element. And so in this case, I really encourage my students, after we've talked about this and discussed it in the board meeting, to go back to their line of best fit and to add a domain like Bradford was using with the colored bars, right? To kind of constrict our equation in this case. So if we go up to our linear equation and we click to the right of the B, we're going to put in our curly bracket, just like you guys were using earlier when you were setting the uncertainty. But this time what we're going to do is we're going to say that this equation only applies when we have one proton or more. So we're going to say protons. So I'm going to type my P and then my greater than symbol and then my equals. So I'm typing those keys separately, although Desmos will combine that into a symbol that says greater than or equal to. And then I'm going to put 1, and then I'm going to close my curly brackets. So now we can see that the line of best fit is kind of starting at that one proton and going up from there. So I think that this helps students to understand a little bit that even though we have a B value, that B value is really there more for the mathematical fit, not because, we can have negative neutrons. So I think by putting a domain on it, it helps us to remember that this is an equation that only applies, when we have one or more protons. Another thing that I want to point out is that in this particular investigation, a lot of times students end up with a C value, that is slightly greater than 1. So usually it's about 1.15 or 1.2, just kind of depending how they do the curve fit. And so another thing is that when they're utilizing the equation, because we can only have subatomic particles in whole numbers, when they go to calculate a number of neutrons or calculate a number of protons, they have to round to the nearest whole number. So that's, again, kind of reinforcing that idea that we are really talking about something in the real world. And so when we model something mathematically and then we apply it to the real world, we have to make adjustments to make sure. All models have limitations, mathematical models included. And so that is a good example of a limitation in this case of the mathematical model, both with the B value and with the decimal of the C value. So that's just a little bit about what's coming up in Unit 2. So I'm going to pause for a second. If you have any questions, feel free to put them in the chat or, just unmute yourself. No?
I don't have a question, but I do have a comment.
Sure.
If you go up into the wrench and click after the name on your labels and you just hit your space bar several times, it'll move it down so it's centered to where it's more closer to the data.
Are we talking about the line of best fit or?
No, the labels on the axes.
Where it says protons and neutrons?
Uh-huh.
So you said to put spaces in front, is that what you said?
No, in the back, following it.
Yep. Great, thanks for sharing. Oh, I guess every time you do the double space though, it wants to do a period at first. So yeah, that'll back those off the ends of the graph if you're needing to bring those labels in. So that was a great tip. Thanks, Tammy. Okay, any other comments, questions before we look at the next graph?
And people are probably already familiar with it, but just because we did that template from scratch, we should have clicked the wrench to add the labels, but most people are already probably familiar with it, but just for completeness sake, I wanted to mention that if that somehow wasn't familiar, yep, that wrench is how you would add the axes labels, and there's a couple other options there too. Yep.
Yeah. Okay, well, let's go on to the next slide. So the next slide here, now we're moving into unit 3, which is nuclear. And so in unit 3, we have plotted the data points again for you. And so let's go ahead and let's turn on all the functions here. And so one thing that is unique in unit 3 is that we are adding a new function. So we have negative linear. So obviously they've seen linear before, but maybe not negative. We have exponential, we have inversely proportional, and then we have negative exponential. So one thing that I notice when students are trying to do curve fitting, like I was saying a few minutes ago, most of them are really going to want to, when they look at the data points here, they're like, oh, it's inverse. So they're really going to want to try to fit it with inverse. And so, the problem with that, and these are the characteristics that we really try to focus on when they try to go to put the inverse curve on there. An inversely proportional relationship will go towards the x and the y axis to infinity. So it never crosses the y-axis, which becomes problematic because in the negative exponential decay for half-life, the first data point is your y-intercept. It is on the y-axis. And so even though try as they may, they're going to try and get the inversely proportional to fit, it just will never hit that data point. It will never go through that data point because it will kind of curve more this way and going towards the y-axis. So, at that point, we want to kind of steer them to looking at like, oh, there's a new function here. Maybe we should try that function. But then a lot of times what students will do is they'll say, well, I can't see that orange function. It's just a flat line that's there at the bottom. And so one thing is that they've kind of been trained over time to move the same sliders again and again. So when you're introducing a new function, it's really important that you take time to say, well, I think we need to look at what variables are in that function. And so, we have to look at the fact that we have n equals n0, and then we have a k and a t. So, that's why when we move A, we're not seeing any movement with the orange line because, the orange line doesn't have A as any of its variables. So again, that's something that they've been trained to do over a long period of time, but it's always been the same variables in the same 4 or 5 functions that they've been looking at. So for this particular one, we want to adjust the N0 slider, and then we want to adjust the K slider. So we can kind of see those peeking out a little bit down below underneath A and B, which is what they're normally used to using for their sliders. So again, I'm just going to give you a minute right now to kind of play with that N0 and K slider and try and get that line of best fit to come into your data points. And we're going to turn off our other functions there and just leave our exponential. Okay, so hopefully you've had time to adjust your line of best fit there a little bit. I did make a goof and I didn't put in my error bars before I did my line of best fit. So I'm going to backtrack just a little bit and do that. So in this particular experiment now, we generate this data using a simulation. And so it, goes through decay and calculates how many, nuclei would be left after each decay. The time is a calculated value. So again, we're not going to have error that is horizontal, but we will have error that is vertical. And so before we used a simulation to generate the data for this experiment, I'm sure many people that have taught chemistry for a long time, we would model this relationship of half-life by using pennies or anything that's two-sided. We'd shake 100 or 200 of those to pour them out on the table. And then, ones that are heads up, maybe those went back in the cup, and the ones that were heads down were considered the decayed nuclei. So anyways, each time that goes through a decay, there's going to be a variation in the actual value that's produced after that first decay. And so that's really where the vertical certainty is coming from. And so with the simulation, it depends on the amount of atoms and that kind of thing. But generally, our vertical certainty is generally around 5 or so. So I'm going to just slide my error bar there to 5. And I always, tell the students, sometimes we forget and we don't make this ending value on the error bars high enough. Like maybe we should have made it go to 10 instead of 5 or 6 or whatever. And so I always remind them that they can click on that far value and adjust what the value of the slider can be. But they can also just type it in as well. So just kind of another handy trick to kind of know when you're dealing with the error bars. So now that I've got that set, now I'm going to go back. And in this particular one, it really helps to set N0 first, because N0 is our number of nuclei, before decay starts. So that is my y-intercept. So I'm going to go ahead and set that first so that it's equal to 0. And then I'm going to adjust my k value. So we can kind of see if I make my k value bigger here, that's causing it to slope down. If I make my k value smaller, it's causing it to slope up. And so we're just going to try and do our best to get it to kind of go through the data points here. That's a pretty good fit. It looks like it's going through the center of most of my points. Oops, and I just moved there, but let me. And so again, with the k value, you can change the increments as well. This seemed like the step increments got me, pretty close. So I think at that point, it's probably pretty good. So now that we have our line of best fit, one thing that I feel like students kind of have a hard time visualizing or realizing in this lab is kind of that concept or idea on half-life. So we've got some sliders or draggable points at the bottom that we're going to drag into our graph. But really quick, let's just put a title in and let's put the mathematical model in before we move along. So this data is actually, so I scrolled down to my data point here. This is beta decay of 100 atoms of iodine 131. And so that's my title. And then also I want to put in my mathematical model. And my mathematical model is a little bit more complicated, than ones have been in the past, but it is that the number of nuclei is equal to 100 atoms that I started with that were radioactive. And then at this point right now, we don't use E yet, Euler's number, because we want to make sure that we're introducing that as part of the lesson. So I'm going to just put in the 2.71. So again, students are not sure what the significance of that is yet, but that will be revealed later in the lesson during the board meeting. And then we're going to raise it to the exponent of negative, and let's go up here. It looks like my k value is 0.11. So 0.11 and then times t. And so I had to use the caret just because when you are doing the labels, I don't think that you can subscript and superscript in the labels. And so just like Bradford was doing earlier, of course, we would probably want to drag our title around. Let me click on the dot here. This doesn't look like it's draggable right now. So I'm going to click on that, click drag, and then probably make that a little bit bigger also. That looks pretty good. Let's kind of drag that. Oops, that dragged the whole graph. Oh, must have lost my drag function there. No, it was on. Drag the point here. And then I did want to actually get rid of the dot too. Oh, there we go. So there's my title and my equation. And then down here is where we see the little half-life sliders. So these are just draggable dots, but they have, you know, a way to show students how many atoms and also how much time. You know, and so we've got one for the first half-life, we've got one for the second half-life, we've got one for the third half-life. So just take a minute and take those sliders and drag them into, since we started with 100 atoms at the beginning, we would want to drag our slider to where we see 50 atoms left, and then drag our slider to where we see 25 atoms left. And then, you know, we can't have, again, 12 and a half atoms, but we can have 12 or 13 atoms. And so we want to drag that slider into place as well. So let me pause for a second and let you do that. Okay, so just FYI, students will sometimes do this with their data points where they will have it on the 50 line for the 50 atoms, but they won't have it reaching all the way out to their line of best fit. So it is important as you're kind of circulating around that you check to make sure that when they're putting the half-life draggable points in, that they actually are going to all the way out to the line of best fit. And one way that they can kind of check that they're out there is that you can interpolate on the graph here if you click on the graph. And so if I'm there where my half-life point is, I can see that I'm there at, well, I'm a little under 25. So let me back it up just a little bit. And then I want to be out to 13 here. Let's see how I did here. Yeah, that's at about 13, so that's not too bad. Let's see where I am here now. It's closer to 25. And so the reason that I really like these draggable sliders is that students can really easily see that the increment or the space in between the X spaces here are all the same. And so if we're looking for the amount of time that has passed for a half-life, we can easily see that, you know, it's about 6.5 days or something here. But what they can dramatically see that's changing is the amount of atoms that we're starting with 100. Now we're down to 50, then 25, and then, you know, 12 or 13. And so that's really important because, again, as they're kind of grappling with, you know, the differences between an inverse function and an exponential decay function, you know, we want them to know that in an inverse function, every time you double the X value, it's cutting the Y value in half each time. But with the exponential function, it's 1/2 the first time, and then it's 1/4 the second time. And then it's, you know, 1/8 the next time, and then 1/16 and so forth, right? So that amount that it's reducing by is continuing to decrease. And I think that by having the draggable dots on the Desmos graph, it allows students to be able to visualize or see that a lot better. All right, so that's a little bit about the different graphs that will be coming up later this semester. I am going to hand it back over to Bradford now, and I think we're going to do a little bit of troubleshooting for when you get into this situation where students are messing with the template and you have to fix some things on the fly.
Yes. Excellent. Sharing my screen here. We don't see the screen I want. There we go. Good. Okay. So this is sort of rapid fire. And if you want to put it in the chat or even unmute, the idea is to go kind of rapid fire here. But here you can tell by the title, it's kind of, you said I couldn't copy and paste my data. Joke's on you. So copy and paste is not easy with Desmos. It is possible. And actually you can see on the left here that a student has done it, but they've lost all their uncertainty boxes and their best fit. Actually, it's just the uncertainty boxes that are lost here. So they just have these green dots. And why? Because when you paste it, it does this thing where it does X2 and Y2. And of course, the uncertainty boxes in this one were set up for T1 and D1. So in any case, it actually is a quick fix. I'll just show it this way to show how it can still go right. We just need to relabel X2 to T1 and D1. And now it doesn't work. Remember that equal sign issue. T1 can't equal a set that's empty and a set down here. So I have to delete the original and then everything's back. So you can copy and paste into Desmos, but it does require a couple extra steps if you want the template to continue to work. All right, so this is that rapid fire here, and I'll try to scroll it. You can look on your own screen or two, or if you have the Zoom screen up. I heard C was 0.3. We've heard this story several times. So their slider's no longer working, doesn't do anything. There's these orange triangles. That's a problem. You actually can look at these triangles and you'll start to see you define C in more than one place. Yep, that's the issue. C is defined here in slide 4, and then they typed in C equals 0.3. Kind of a clear sign that they heard C. They didn't actually find C themselves. They heard it was 0.3 and they typed it in. So solution is they need to delete one of them, maybe that first one, and now that C is back, it can now equal just one value and our sliders work. Just checking the time. All right, I'll give a little bit more time on this one just to kind of let you hunt. This one, just that, you're right, Desmos doesn't work for me. So here you go. They're trying their slider, nothing's working. This one's kind of interesting. These circles look a little different. There's a D equal something. That's a telltale sign. And I'll just pause to give you a chance to actually see if you can sort it out. Okay, it's definitely weird that it's giving us this gray box. There's times where we want that gray box, usually not in a lab setting, but in teacher Desmos we'll talk about sometimes. Anyways, that's kind of weird. Normally we don't see that box. So it's saying D actually equals something. How's that possible? We actually go over this with students a lot, that C is a constant. That's why you can plug in a number. And then, but here it's actually saying, oh, T must have been defined. And yep, if you look down here at line 7, there it is. The T is supposed to be a variable. We can't set T equal to 0.3 and also think Desmos is going to vary it. That's that equal sign issue that we talked about. So as soon as I delete that T equal to 0.3, it's allowed to vary, and we get our graphs back. And again, in that rapid fire fashion, let's try another pretty common one. Here, the uncertainty boxes are broken. So again, here they're going, and their C works just fine, but their uncertainty boxes are broken. And this one's a little bit harder. We see this a lot though, for us later in the year. And actually, the uncertainty boxes are not broken. As soon as, when you turn that over, that they have to set the size of the uncertainty, then they actually just left them at 0. So the boxes were there, they were just infinitely small, 0 small. So in any case, once you decide to start having students unhiding these and having students set the uncertainty, just be aware that's just one of the most common issues we see. So they weren't broken at all. Okay, this is the last one that I'll do, and then I'm going to hand it over to Joe May for a couple more. But here, you should never have this happen, but somehow it occasionally does. You're just looking at it. I know Jermaine hinted at it, wiggle the C, gray box, everything looks good there. Check T1, D1, okay. They got uncertainty bars. It is, nothing's wrong. What is going on? Except for, yes, let's check the not for editing. And all of a sudden you're seeing orange triangles pop up. At this point, I actually suggest a student should just start over with the template. Diving into
This
this,
is a lot of fixing.
yes, that could take you 5 minutes to just find what the problem is. So at that point, maybe just they need to start over. But I call it a good problem to have, right? Here was a curious student that wanted to see how that worked. And you can also see for us, because we, U horizontal, that kind of makes sense. U for uncertainty, horizontal. When in our template that we made, I didn't want to make you keep writing horizontal like 5 times over. So we just had that be V for vertical uncertainty. But in any case, yeah, you can see it. You can see how it works there. But in any case, student wants to look at that. That's awesome. But troubleshooting that, probably not worth it. So just start over with the template. Okay, with that, should I stop my screen share? How do you want to do that?
I'll take over.
Yep.
All right, here's another situation that we see a lot when we are working in the classroom. So, again, students will be moving the C slider and they're like, well, one line is moving, but the other line is not moving. And, the other line that's not moving inevitably is the one that, they need to get moving. So when we look down the list here, one thing to kind of look out for is that you'll notice that in the blue quadratic function, right, it still says D equals C, so it has the C in it, T squared. But then when we look at the red function, it says D equals a number, 0.88, right? So again, they might have heard somebody at their group or somebody in the class say like, oh, the C value is 0.88, and then they took out the C and just put in the 0.88 or whatever, which might be appropriate for, the adjacent tables data set, but might not actually be appropriate for their data set. So, again, the way to fix this is to get rid of that fixed value and put back the C there. So once we put back the C, then the lines will kind of track together again. And then, of course, we'd want to probably get rid of that blue one. So that's definitely something that we see a lot is students typing in the actual equations themselves and taking sometimes the C slider or the B slider out. So here is another one. So I don't know if you noticed earlier, but when I was doing the curve fit on the negative exponential, the curve fit wasn't exactly correct. So one kind of trick of the trade for students that are like, no, I really want to, get it perfect, or I really want to get it, the best that I can, is so that when I'm going to, turn off the blue line here for a second, when they are doing their curve fit. And so in this case, you can see that the step size is pretty big. So that's, problem in and of itself. So I can click on the number up here. It says the steps are 0.5 right now. Maybe I'm going to change that step size to 0.1. Click off of that. That's going to just make those lines a little bit more smooth. But again, these are not perfectly lining up. So, we probably want to try and make them at least go through the error bars as much as we can. And then we want to, we can type here too. So if we're wanting to get a little bit more or a little bit less, I always tell students that the slider is supposed to kind of get you close to where your line of best fit is, but then you might need to fine tune that line of best fit kind of by typing a little bit, at the end there by adding another significant figure, or maybe taking it down, or taking it way up. So that's also a nice little trick also to kind of do a little bit more fine tuning, because the steps can only sometimes get you so close. That's a little bit on that one. And then let's see. So the next one is probably the one that I encounter the most. So our students have Chromebooks with touch screens. And so a lot of times with the touch screen, accidentally, they either zoom way out or they zoom way in, and then like all of a sudden now we can't see your data points anymore. And so if we press on that magnifying lens, that'll kind of recenter our data points. Now, I don't feel like that ever, gets it perfect to where we would want to, but it certainly gets it a lot closer. And then like Bradford was saying, if they have a touch screen, actually on a touch screen, just so you all know, on the Chromebook touch screens, they can actually touch the x-axis and stretch it apart, and touch the y-axis and stretch it apart. I don't have a touch screen. So again, if I hold down shift, I can do that same thing that Bradford was talking about earlier and kind of stretch my graph out a little bit. And I'm the same way. I like mine to be kind of a little bit there. So. And then one thing that we've started to do to the templates is we've started to lock the viewport. So on the exponential decay one, though, that's very difficult because the two isotopes that we're looking at in that case are iodine and plutonium. They have very different half-lives. So this is one where we generally have to scale it for plutonium, but then the students that have iodine have to use that magnifying lens. But once they've got it in the spot, to prevent it from moving any further, they can press on the wrench in the top right-hand corner, and then under more options, they can click lock viewport. And so then it won't change. And this is really important when you go to, especially like with the Gay-Lussac's law, since you have some groups there that have like 25 particles, and then you have other groups that have 50 particles, and you really want students to see that difference in the slope, that the pressure is twice as much when you have 50 particles as 25. You want to lock that viewport so then when they're comparing their Desmos graphs side by side, that you can visibly see that difference in the angle of the slope. So I say, if you can, lock the viewport ahead of time on your templates, and that's going to probably just, make it a lot easier for everyone. But if things get out of scale, you can always press the magnifying lens and that'll bring you back. Okay.
Nice. We have the option to just briefly show the exam questions. I did pull.
Oh yeah, that's right.
I have it open too. I don't know.
Okay, why don't you share and I can just talk about it.
And yep, I just gotta get my screen share on. Yeah, analyze. Yep.
So one thing that we were finding at Mountainside is that students were getting all the way to biology, and some of them had never made a Desmos graph because they had borrowed their friends or, done whatever, but they hadn't actually developed that skill of graphing themselves. So when Classroom Desmos came out, which was then called Teacher Desmos, last year, what we started to do is started to have some of the graphs that they're producing throughout the year for them to be done in Teacher Desmos, or excuse me, in Classroom Desmos. And so some of the nice things about that is that you can see each student working in live time. And so if you see an error that's like happening on your screen, immediately kind of like who to move to give them some help if you see things going sideways really quickly. This was a test question actually that we're looking at here for Unit 1, where students graphed some, I think it was hurricane data, and then did their negative linear regression here. And then I think on the exam had to do a calculation with their with their equation that they put here. But so it's a really nice way to like see actually where each student is with their graphing capability and with their graphing skills, because it puts them in the situation, in this case, because it was a test question, where they actually have to do it on their own. So, that was one way that we used it. And then I think Bradford, if you want to go to the other example that we talked about, we also used it later in the year. Let's see, do you have the other one?
Yeah.
The half-life graphs. We also used it later in the year where we just had students, because the half-life graph is a fairly complicated one, and so is the pH graph. We just had them actually for the lab do their graphs in the Classroom Desmos. So, you know, again, another feature that you can use with Classroom Desmos is that, you know, sometimes you can overlay graphs on top of one another, right? You can look at graphs with students in class. Like right now, my students' names are, you know, it's set to anonymize. So nobody's real name is showing, it's filling it, I think, with all mathematician and scientist names and that kind of thing. Bradford, do you want to talk any more about like overlaying the graphs? I don't know how much you have done that, but.
Yeah, we do it quite a bit. And that is, it's a really nice feature. And basically you see the outcome here. This was just a single data set. So all the lines are over top of each other. But if you do that jigsaw, it can be really powerful. And that is actually something we'll talk about at that Teacher Desmos webinar, how to set that up, how to set this up. So this is a little bit of teaser. It turns out this is very easy to make, but it just takes a little time because you got to give a unique web link to each class period. So that's where the trouble with Teacher Classroom is that each class period, well, turns out, yeah, turns out once you make your classes, then you can just assign it. But yeah, that's why that's a little bit more beyond what we were going to do in this one, because this webinar is about the actual graphing tool. And then on October 10th, we'll talk about how to use Teacher Classroom so that, again, just as Jomei said, you can peek real time. So that I can go back to, I'll turn off the overlay. You could see students working real time as they're working through this. And again, one last thing just to show it. Well, this is a good one. So you could show this student and then you can show this student and you can jump in. This is not like Google Docs. So this is your own one. If hey, we want that title to be a little bigger. So I could go find their title and model, demonstrate for them. Hey, you go down to the A and change it to a 3. Okay, that was too big. 2. Yep. So you can help students pretty quick, and then you could go, this student has something. So that's the teaser for the October 10th Teacher Classroom one.
Yeah. We try to do it at least a couple of times a semester just to, again, kind of hold that accountability level high to make sure that students are actually developing their graphing skills, because again, they're going to go into biology and the graphs in biology are going to get even more complicated with Gaussian and, you know, other functions that they're using there. So
nice. Okay, well then we got really just 2 last things to show off. So now we're kind of getting to the advanced features. And so that's going to be on slide 13. We're on slide 13, so I'll jump there. And this one is nice, and it's not, you know, this is not core curriculum, but sometimes just again, the students learn Desmos, and sometimes you might want to do this as a teacher. Sometimes we want the computer to find the best fit, right? So the patterns approach really has a strong preference for students. That is just that kinesthetic learning, and that is that sense of ownership of the best line is really powerful. So we like it. But did want to just one time show you in the advanced time, you got student doing science fair and they're already comfortable with Desmos and they want to use it. Probably for science fair, you want to let Desmos find the best fit line. So here we go. We got this one. And maybe this data right here seems to be, you know, quadratic or linear. Yeah, it seems to be quadratic. Okay, but here's my best fit. You know, something like that. Yep, I'm a little high, a little low. Okay, so I need a new line. So I showed return, so I'll go up and hit plus and just put expression. Now, so I'm going to try to explain it to help you remember too, is we now want to fit not for a generic D and T. We specifically want to fit our data set, right? That's the key word, our data set. And sets are D1 and T1. So I'm going to set this up as D1, and you think equal, but equal's already used. And so the thing you just got to know is they use tilde. So that's the other key. So now I'm telling Desmos, hey, I want you to find the best fit. So I use that tilde. And C is already used, right? We can't have C. I can't say C is equal to 0.32. So I need another letter. I still want to use C for constant, but I'm going to use capital C. That, remember, it's case sensitive. So lowercase c and uppercase C are totally different variables. And then, of course, I want to do T1. That's the data set that I'm looking at, T1 up here. And I do want to make it quadratic. So I'll do that Shift 6 to get into superscript mode, tell it to fit it with a quadratic. And look, it's actually not much different than what we did with the slider. All right, so you do get some statistics there. One last feature that I do, or with the regression, it's just right here, so why not show it? So in any case, let me say the big picture idea. Like, we found the capital C to be 0.32, and I didn't even try that hard. That was pretty quick. They found it to be 0.3129. Yep. So that's just another reason why we really do think that the slider is the way to go in most cases. All right, but it is right here. So you can just see, sometimes we see this, there's some physics labs, and I think there's probably chemistry labs that might happen the same way. Just a couple, not every lab, it's good for this. If you have systematic error, right, you can see that the data point is above, 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 at, below. This data was a ball on ramp, and we picked this one because that's somewhat intuitive. So this ramp is bowed. So think about it. If it is going too fast at the beginning and then too slow at the end, how is the ramp? Is that ramp bowed down or up? And I might lose you with no visuals on that, but just think, if it's going too fast, oh, that's a sagging ramp. And you see that, and they have a built-in feature that if you plot the residuals, which is how far the best fit is from the actual data point, I'll just turn that on, and you can see that for the first data point, you have to go up a little bit. So the green, that second, I'm going to change the color on this. So I'm going to make it purple. So yeah. Oh, that changed the line. I wanted the residuals to be purple. But in any case, you can just see they're green, so they match. This one was way off, so the dot's really high. This one's basically at the line, and this one is below the line, so it's below the x-axis by the corresponding amount. So that's just a little built-in feature that if you do have a systematic error, it helps you visualize that. So that's the pre-built-in find the best fit and the residuals. All right, so just one last thing to end on something fun, and this is another one that lots of times I might teach in the last 5 minutes to a period that gets done early, and then it's fun enough, and some kids take this really far, and then students in other periods, hey, why don't we get to learn colors? Well, then, okay, let's learn how to add colors. So there's those built-in features, and it's just those, 6 colors, and they're good, but sometimes you want more than that. All right, so we do need a variable. The only way to have a new color is to have a variable hold it. Now, we've already used C a bunch of times, so I'll show just another way of using a new variable with C. I'm going to do C subscript 1 for C for color, subscript 1 equals, oh, it doesn't like that, so let me check. Okay, that's okay. All right, so this is that one where I told you RGB for red, green, blue has to be lowercase, parentheses, and now we got to tell it, and you got to know a little bit about computers and binary. 8 bits has 256 colors, but they start at 0, so the scale goes from 0 to 255. So I'm going to just do 100 red, 200 green, and then how much blue do I want? Only a little blue, so I'm going to do 55 blue. And then you can see the color. It's that green color. It's kind of a fluorescent green. All right, I'm going to back off my red. I'm going to take it 100 down to 10, so it's making it even brighter green. And now, if I go back up to my best fit line, and I click and hover on that blue, there's that new green color down there. And as long as I leave C1, it will stay. So I'll pick the green, and you can see my best fit line change to that fluorescent green. I have to kind of zoom in a little bit. But if I go back and change this later, let's say I take the green down to just 10. Whoa, it changes it to black. I'm going to bring up the blue by going up to 255. Whoa, see how it's actively changing it. So if you want multiple colors, we need multiple ones. So I'm going to make a new one, C2 equal sign. Now, Desmos has like an art competition where students make it. And that's actually, we were talking with our art teachers, and that's how we got started on this. And they kind of made fun of us for using red, green, blue, like only science, engineering people, right? Like monitors are red, green, blue. So red, green, blue does make sense. That's your digital cameras, your monitors, but lots of times it's a little bit more intuitive for a lot of students to do hue, saturation, and value. So HSV. So hue is what color do you want, right? So again, that's 0 to 256. So let's try out like 1. And then that saturation, we of course want it to be saturated to see the color. But again, if you want to do that shading or lighter shades, and then value from 0 to 1, the intensity. Okay, so 1 starts off as red, and then I'm just going to change the hue to 100. So that takes you to the green. And then of course, if we go to like 255, we're just going through the colors, red, green, blue, and then maybe I back off and do like 177. Okay, there's cyan even. So there it is. And again, if I go back up and go to that best fit line, oh, the best fit doesn't give me that color option, but all the things we added will have that color option. So I can change the best fit and it will be cyan. All right, so that was just one of our advanced tips that just is kind of fun, and it's not high stakes or anything, but just something you can show students. This itself just generates lots of questions. Red, green, blue monitors are like that. And yep, they've heard that in in science classes probably, but some kids heard it and forgot, all that good stuff. But anyways, it's always kind of fun to add some new colors to the graph, and that's how you do it. We do got just a couple minutes left, which we really want to just give to you to do the exit ticket. Right, that Oregon Department of Education money really requires that of us, and so we hope you'll take a moment to just complete the exit ticket, and that's right on the paid time. With that, we'll do a quick check on the chat just to see if there's any last questions for this session. All right, well, if not, we'll start to wrap things up here then. Joe, any last comments?
No, thank you all for joining us tonight, and we hope you all have a lovely evening, and hopefully things will settle down in the school year soon. We all know the beginning of the year is like drinking from the fire hose, so